Hey, good morning, guys. Assalamu alaikum. I hope that you guys are doing well. Welcome back to grade 11 mathematics by Inspired Teens, where in today's lesson, we are going to be continuing with Euclidean geometry. Fun stuff. Okay, please confirm that you guys can hear me and that the audio is working and you guys can see my screen, you guys can see me and everything is cool. Okay, cool, perfect. Thank you. Everything seems to be working fine. Cool, cool, cool. Okay, so let us just recap what we've done so far. I think we ended on, what did we do before this? Okay, whatever topic we did do before this, but we started on Euclidean geometry. And if you remember that I told you that we're going to start from basics. Okay, we're going to try our best to master all the basics, make sure that our understanding of all the fundamentals are on point. Okay, they're on par, on the level they need to be in order to answer all the difficult questions. Okay, so that's the plan. Okay, so the first thing we discussed was exterior angle of a triangle. Okay, and we discussed how to calculate it. We discussed what is an exterior angle, right? Don't confuse things that are not exterior angles. And you will see examples in difficult Euclidean examples, things that are not an exterior angle, but like look like an exterior angle, and then you confuse it for an exterior angle. Okay, so that's why we need to know this. Okay, so you need to be aware of it. Remember, it's the straight line continuation of one of the sides of a shape, any shape, in this case, a triangle. Participants can now see your application. No idea what that means. Okay, so, okay, cool. And then we said, how do we calculate it? It is actually the sum of the opposite two interior angles. Okay. Okay, cool. So let's have a look at this. Then we discuss parallel lines. Okay, and a few important things there. First obvious thing is fun, right? F, corresponding angles, cointerior angles, alternate angles. Okay, remember the F can be flipped. Its orientation can be anyway, right? Cointerior angles, that forms kind of like the U or like an N or a C. Okay, it can be flipped anyway, but we just, in this case, we form a U. And then the Z or the N, that's alternate angles. Again, the orientation really doesn't matter. We just learn it with fun, just so it's easier to like remember or understand. Then we discussed a very, very important line that many of you perhaps never even, maybe you've never heard of it before, maybe you've forgotten about it, you haven't been taught in recent years, the transversal line, which is important, and you'll see how it will actually help us to actually to use our parallel lines in a question to their maximum. Make sure that we get all the angles that we should in a parallel line, just knowing and identifying its transversals. Okay, so we learned that line. Just to recap, what is a transversal? A transversal is a line that basically cuts through both parallel lines, or at least touches both parallel lines once. And we looked at these like 4 examples, different cases, just to be a bit extra and specific. Number 1, it goes through both. In number 2, it just goes through one and touches the other. In number 3, it touches the other but goes through the other. And in number 4, it's just touching both, but all are perfectly fine. All are transversal lines. Okay. Cool. Then we moved on. We discussed Pythagoras' theorem, which gives us the equation hypotenuse squared is equal to adjacent squared plus opposite squared. Okay. And what is the hypotenuse? Hypotenuse is opposite to the 90-degree. And then depending on which angle we work with, so in this case, we chose to work with that angle. We have 2 options, that angle or that angle, depending on what the question gives or the question wants. But if you're working with this angle, then opposite this angle would be referred to as opposite, and adjacent to that angle would be referred to as adjacent. So we just keep that in mind. Okay, I said, please don't make the confusion. If you are given the hypotenuse and one of the sides, so like the sticks here, you have the stick here and the stick, you have hypotenuse and you have adjacent, and you don't have opposite, and they want you to calculate it. Just rearrange this first equation. Don't assume, this is what you should not assume, that opposite squared, for example, is equal to, you just add them all the time. I don't know why, but many people just assume this, that you just add them all the time, and this is incorrect. Okay, you're just adjusting the first equation, rearranging it, right, to leave opposite alone. It's not adding. You actually end up subtracting it. Hypotenuse minus the adjacent. Or if you want the adjacent, then hypotenuse minus opposite, all squared. Okay, and then to get your final answer, you square root and all of that good stuff. Okay, so okay, that's just the example. Let us move on. right? Let us discuss some circle theorems, okay? And then we're going just to, not some circle theorems, but just some understanding, some concepts and understandings that you need to have within circles so that we can actually get to the theorems, because that's what we're going to discuss next. We're going to start going through each theorem to understand each theorem. So let's look at this first circle, and this is basically displaying chord AB. Okay, and what is a chord? A chord is essentially a line within a circle that touches any 2 points of the circumference. A chord is a line within a circle that touches any 2 points on the circumference. So this AB, this guy is a chord. We can call this CD. CD is a chord. Okay, let me just. Okay, so just keep that in mind. Important for us to understand. Of course, I'm sure you've seen even if you've done basic Euclidean, you've seen the word chord like 500 times, right? Because so you need to understand what a chord is. A chord is basically a line that touches the point of the circumference twice. It's a straight line drawn within the circle. Okay. Then when we look at this key word that many people struggle to understand, chord AB subtends. What does the word subtend? Subtend, to subtend an angle. What does it mean? Okay, we'll write it with regards to the angle in a second. But let us talk about this. Chord AB subtends. Okay, so I'm going to complete this diagram. So we have the same chord AB, but now I'm going to create an angle from AB to D. I created an angle. I've completed the lines, and I've created angle D. Okay, we can call it theta. So angle A, I think you can all agree with me that angle theta was created by the lines drawn from A and from B towards D. Okay, I think we can all agree on that. Angle theta is created by drawing the lines from A and B towards D. Okay, and in that case, we can sort of say that like chord AB creates angle theta, right? Because it originates from chord AB, right? If it originated from another point, like for example here, it would create a different angle, right? So chord AB actually subtends. Okay, I gave the final secret away. Chord AB actually creates angle theta. Okay, and that word creates can just be replaced with the word subtends. Okay, and it means the same thing. It implies the same thing. So basically, chord AB subtends angle theta. Okay, I'm actually just going to write that angle D. But let's just write angle like that. Which I just gave a value of theta, but angle D is fine. Okay, so I hope that's making sense. If anybody's still confused as to what the word subtend means, please let me know and I'll go through it again. Okay, so chord AB, this chord, which is a line that touches 2 points on the circumference, you join them, of course. You don't actually, I'll show you in a bit. I think I show you. Well, no, I'll have to show you now. All right. Chord, you see that chord AB, it subtends angle D. It creates it. So which chord is angle D subtended by? Angle D is subtended by chord AB. Okay, so those are important things, and you'll see it's important to understand like where does that angle come from? Which chord creates that angle? Or which chord subtends that angle? Or which chord is that angle subtended by, right? These are questions you'll be asking yourself when it gets more complicated. That's a basic that's important to understand. Okay, so that's the first angle. But now chord AB, I can go from chord AB okay, let's just try our best to align these. Okay, I can go from chord AB, I can also go to C. There's nothing stopping me from doing that. And as you can see, no pun intended, I have created another angle, and let's call that alpha. Okay, so chord AB has now subtended another angle at point C called alpha. Okay, and we learn later on that actually these two angles are equal. when a chord subtends multiple angles, or any angle subtended by a chord, any angles subtended by a chord are equal to each other. Okay, but we'll learn that in a bit. But the main thing here we need to understand and take away from this diagram is the word subtend, and what does it mean when a chord subtends an angle. Okay, so by the way, this chord does not have to be drawn. Okay, that can be a bit tricky. So when it's drawn, you can easily see, okay, it's subtended by chord AB because that chord is drawn, and here it's in different colors and everything's fancy. But when everything's black and white and that's chord, it can get confusing. Okay, so just keep that in mind, that the chord does not have to be drawn in for you to be able to tell that, okay, I can see that C and D, or angle alpha and theta, are subtended by chord AB, because you know a line, you know that a line joining these 2 points would form a chord. And they both, C and D, originate from A and B. Okay, so I hope we are on the same page up until now. Okay, cool. That's that. Okay, so just remember the same chord, and then I'll just write here, actually, alpha is equal to theta, but we'll do the actual theorem that tells us that. But for now, alpha is equal to theta. So you can guess angles subtended by the same chord are equal, right? That's sort of the reason that we give. Now let's move on here. Let's look at this circle. We have, is the screen a bit blurry, or is it okay? Is it like slightly blurry or something? Or is it legible, or is it unlegible? It's okay. Okay, cool. Perfect. That's good. Okay, so let's look at this, just discussing something that we probably should know already, but we'll go through it, right? Radius and diameter. So we have 2 radii actually, right? And of course, radii are equal. What is a radius? A radius is point from the center of the circle to any point on the circumference. So for example, I can easily draw another radius here. This is a radius. Sorry. Okay, that's also a radius, and they are all equal. Okay, because the distance from the center to the circumference, no matter where you are in the circle, is always going to be equal. So remember that the radii are equal. Let's get rid of this guy. Okay, remember that the radii are equal. Let's just leave that there. The radii are equal, and 2 radii. So if you draw a continuous line that forms 2 radii like this, okay, the entire distance, 2 times the radii is equal to the diameter. 2 times the radius is equal to diameter. Okay, so just keep that in mind. Learning radius and diameter, a bit of a more easier concept. Let's have a look at this. Equal chords subtend equal angles. So let's just say we don't have the same chords. Okay, we have 2 separate chords, like here in this case, AB and CD. However, AB and CD are equal in length. Okay, so what does that tell us? The angle that's subtended by chord AB, okay, to E, and the angle that's subtended by DC's to, that point is not labeled, we'll label it in a second. Let's call this A, B, C, D, E, F. Okay, these angles are both equal, so I'm going to call this theta. I'm going to call them both theta, indicating that they're equal. Okay, why are they equal? Okay, because the chords that they are subtended by are equal. So equal chords, irrespective of where they are, they don't have to be the same chord. It makes sense, right? Because if we say that when angles are subtended by the same segment, they're equal. The same segment means that the chords are equal technically. Sorry, when angles are subtended by the same chord, they're equal. If we consider the same chord, that same chord is equal in length with itself, right? So in this case, if we just do 2 separate chords that are equal to one another, same concept applies. The angles which they subtend would also be equal to one another. Okay, so just keep that in mind. We can say here that angle E is equal to angle F, and this is because they are both subtended by the same chord. Okay. I hope that's making sense. If anything you want me to explain or slow down, just tell me. I'm going to draw another chord here. Okay, and we're going to discuss the concept of segments. So when you draw a chord anywhere in the circle, all right, you basically separate your circle into two segments. A segment here, we call this segment 1, for example, right? There's no specific name for it. Segment 1 and segment 2. Segment 1 and segment 2. So that's what you need to know, basically. When you draw a chord or any chord in a circle, separates a circle into two segments. Okay, that's a bit confusing. Okay, we'll go through I'll go through this in a different circle where we'll draw it in two separate circles. Okay, so yes, basically a chord separates a circle into two segments. That's what you need to understand. This is referred to as a segment. This part here is referred to as a segment of the circle, and this is another segment of the circle. So you don't just get segments unless you separate it by the chord. Okay, so just keep that in mind. So let's go through this theorem again. Okay, so in this case, I'm going to draw a line here. And in this case, I'm just going to draw a line here. Okay, and I'm going to say that these two are equal in length. They are equal in length. So if like one is 5 centimeters, the other one is 5 centimeters as well. And for each chord, I'm going to subtend an angle. So I'm just going to subtend this angle here. Okay, and I'm going to call this, we'll label it. Okay, we call this point A. Okay, and it subtends that angle. And this equal chord, this blue chord and this pink chord, they are equal. Okay, and just say it subtends this. And I'm going to call this B. Okay, so that would be referred to as angle B. Okay, that's point B. So in this case, right, you can see that we have two equal chords. How do we know they're equal? By this annotation here, they're equal in length. Okay, and in two different circles, right? But because these are equal chords, and then I'm just gonna write a little thing here to say these are equal circles as well, just for this thing to be true. These are equal circles. And you can use as you see, I copied and pasted the first circle, so they have to be equal in length. Okay, so equal chords in two separate circles, okay, equal in length, each subtending their own angles, creating their own angles. The pink chord subtends angle A, and the blue chord subtends angle B. But because these two are equal, okay, this is important now, because this pink chord is equal to the blue chord, that indicates to us that any angle subtended by those chords are going to be equal. So basically, angle A is going to be equal to angle B. And the reason for that is because they are created or they are subtended by chords which are equal in length. Okay, they are subtended by chords which are equal in length. Okay, I think we can move on from that. But I hope it makes sense. Excuse me. Will the equal chords be in the same circle or two? Generally, they'll be in the same circle. Okay, I just did it in two different circles just for the understanding. However, you could actually get a case like this because remember, if they are equal circles, consider this, right? Look at what I'm about to do. If they are equal circles, technically, I could take this circle and put it directly on top of that circle, and now they're the same circle. Okay, they're now the same circle. So if they're equal circles, the theorem would work as well because it's like they're the same circle. Okay, it's just now if you're going to take equal circle and put it separately, it's literally the same thing. Okay, so that's why it would work. It wouldn't work in unequal circles, of course. Okay, just because In unequal circles, obviously things change, right? You will be able to get the same chord, but they're not going to subtend the same angles, whatever it is. Okay. So yes, generally, however, they'd most likely be in the same circle, but they could ask you a question where they give you equal circles. So just have that understanding as well. Okay. Again, equal chords, these chords are equal in length. They could, like, let's say, for example, like I said, they could be like 5 centimeters each. In Euclidean, length like that doesn't really matter, but I'm just telling you, right? They're equal in length. So the angles that they subtend would also be equal to one another. Okay. And again, doing it in separate circles, doing it in the same circle, same concept. Okay. Let's look over her. Let's talk about theorem uno, theorem 1. Okay. Line from center perpendicular to chord. That's what this is saying. Line from center perpendicular to chord. A line drawn from the center of a circle perpendicular to the chord bisects the chord. A line drawn. Okay. A line drawn from the center of a circle, which is perpendicular to that chord, bisects. Okay, let's learn it on our own. Okay. Now I'm going to highlight what's given. Let's make this 1 second. That's perfect. Okay. I'm going to highlight what's given. So we'll read the theory in a bit. Okay. I want to do this practically first to get you to understand. We have this little contraption. I'll explain what's going on. But what's given, okay, what's given is going to be in red. Okay. So this is given. The question is given like this, or a diagram is given like this. Okay. What is it? What does that mean? That basically means, okay, that indication tells us that JK is equal to KL, okay, in length, because they give us that annotation with the lines. Okay, that means sides are equal. Now, if you'll notice that this line from the center, O, is actually going to be a radius if it is continued right till there. But where it touches this chord, okay, where it touches this chord, it is the point that's halfway between JL. It is K, it's point K, okay, which actually splits JL into 2 halves. So in that case, we can say that OK bisects JL. Okay, so OK cuts JL into 2 equal parts. I think we can all agree on that. That's what these lines mean. OK cuts JL or bisects JL into 2 equal parts. Okay, and it happens to be that OK is a line from the center. Okay, it's like a radius line, or it could be a diameter line. Okay, they don't always complete it to K, but they also, a lot of the times, they'll write it as the long radius here, right, and expect you to understand the same concept. Or sometimes they could even draw it as a diameter. Again, same concept. It's a line from center. Okay, so I hope that's all adding up. So here they just opted not to draw a full radius or a full diameter, to just draw from O to that line. Okay, to show you the concept. So what's given is that OK, or the line from center, bisects this chord. Which chord? JL, chord JL. Okay, so the ruling is when a line from center bisects the chord, it is perpendicular to it. That's the rule. When a line from center bisects the chord, it is perpendicular to it. Here's the reasoning. Line from center which bisects chord is perpendicular to the chord. So if it happens that it is it bisects the chord, always 100% of the time, it is also perpendicular to that chord. Is this thing skewed? It is skewed. Okay, so I hope that makes sense. If a line from the center touches a chord and it bisects it, you should know that it's also perpendicular. Let's look at this instant. What's given again is going to be in red. So what's given this time is that the line from center, here they drew it as a full diameter. Do you see that? Even past the circle, but it's the same concept because it's a line that's coming from the center that's going to cut through this chord or touch this chord. So the line from the center, what's given is in red, keep that in mind, is perpendicular to this chord. If it is perpendicular, it would then indicate that it also bisects the chord. So what's given is in red. What's green is what you can deduce from what's given. What's given is in red, and what is in green is what you deduce from the given. So what's given is that the line MD is perpendicular to PT, and from that you can conclude that, okay, since it's perpendicular, that means that line MD bisects chord TP. And here's your reasoning line from center, which is perpendicular to the chord, bisects that chord as well. So just keep in mind what's given. In this case, they both work the same. They like the same theorem, just like slightly different, because if it's perpendicular, it bisects. If it bisects, it's perpendicular as well. Okay, that's what you should know. But yeah, this is the case when it's given that it bisects, and this is the question where it's given that they are perpendicular. Okay, let's read all the mumbo jumbo. A line drawn from the center of a circle perpendicular to a chord bisects the chord. We know this because we're smart. Circle center with O, blah, blah, blah. Let's just throw in this to say that it bisects. Okay. Converse theorem. So we'll do all the converse theorems, which basically you'll see as we go along, you'll understand them. The line from center midpoint chord, the line segment joining the center of a circle to a midpoint of a chord is also perpendicular to that chord. Okay. Converse of theorem 1, perpendicular bisector of chord. The perpendicular bisector of a chord passes through the center of a circle. Basically saying that if it's perpendicular to the chord, then it also bisects the chord. Okay, perpendicular bisector means it's both, a line is both perpendicular and bisects another line. Okay, let's move on. This one is theorem 2, which says angles at center, that little annotation represents angles. Angles at center equals 2 times, that's a multiplication, 2 times angles at circumference. Angle at center is equal to 2 times angle at circumference. The angle subtended by the arc at the center of the circle is twice the angle the arc subtends at any point on the circumference of the circle. Okay, let's have a look at this concept with this diagram. Okay, this diagram, we have points A, B, C. Okay, and the chords A, B I'm going to join to actually create the chord. Okay, so now we have chord A, B drawn in. Okay, and as you can see, okay, if we initially ignore this guy, okay, if we ignore that, right, you can see that chord AB subtends chord AB subtends angle C. Chord AB subtends angle C. All right, that's clear. And now what we're going to we're further going to state that C is actually what we call a circumference angle. Why is it known as a circumference angle? It is a circumference angle because it is at the circumference. Wow. English. Okay, so chord AB subtends angle C at the circumference. And if we get all of this back, we can see that chord AB actually subtends another angle, but it's not a circumference angle. This is a center angle because it's at the center. M is the center. They'll tell you explicitly with no ambiguity that M is the center. So chord AB is subtending 2 angles now. Okay, one is at the circumference and one is at the center. Okay, and these are actually the angles that we are talking about. Okay, so it has to be, so when we say angles at center equals 2 times angle at circumference, yes, it means that an angle subtended at the center, okay, is actually twice as much as the angle that is subtended at the circumference. What's important here is by the same chord. Both your center and circumference angle need to be subtended by the same chord. Otherwise, it's not going to work. All right? Because, okay, they have to be subtended by the same chord. okay, for this theorem to be true. Please keep in mind, always try to remember it like this. Just remember the center angle is bigger, because now you're going to do this, you're going to confuse, and you're going to see the 2 times at the circumference. So you're going to think that the circumference is 2 times the center. But no, think of it like this. Angle at center is equal to 10. And angle at circumference is equal to 5. So you have to multiply it by 2 to get there. So 2 times 5. So because you have to multiply the circumference angle by 2 to just get to the center angle, that already tells you the circumference angle is smaller. Okay, so just always remember that the center angle is bigger. So the angle at the center is twice as much as the angle at the circumference. So to get from the angle of center to circumference angle, you divide by 2. Okay, because circumference angle is half of center angle. Okay, so yes, they've got to be angles subtended by the same chord. So in this case, as you can see, angle M is subtended by AB and angle C is subtended by AB as well. So if we have to give a value to MX as 2x, sorry, as M as 2x, okay, this is the angle at the center, subtended by AB. So the corresponding angle at the circumference subtended by AB would be half the value of the angle at the center. So if the angle at the center is 2x, the angle at the circumference is x. If the angle at the circumference is x, the angle at the center is 2x. Okay, let's just do some other weird examples. Okay, let's do like one more other one. Okay, so let's just have, again, these chords don't have to be drawn in. Like I'll have A and B. Okay, so let's just say my center is there. And now I draw in this line. And this is a center angle, okay, subtended by, let's just pretend that's the center, right? This is a center angle subtended by AB. And any other circumference angle could be, oops, it could be here. Bad choice. Could be here. Okay, that's also a terrible choice, geez. Like maybe there, wherever, right? And then maybe another one could be here. Yeah, this one. Yeah, this is the example. Okay, if you notice, they might be a bit weird to look at. I'm going to call this X. All of these I'm going to call X. And then this is also X. But then this one at the center is 2X. Okay, so look carefully, right? The one at the center, which is subtended by AB, that's 2x. We gave it a value of 2x. And then if we wanted to get the value of its corresponding circumference angles, we just have to half it. Okay, so yes, look at these. So it's not always easy. It's not always like straightforward that just looks like this. It looks perfect and you're going to see it every time. Because it's also true for the pink circumference angle. So if this didn't have to exist, that you'd need to be able to see that. Okay, you need to be able to see that. This angle, let's call it at O, and this angle at C. Okay, they are a center and a circumference angle subtended by the same chord respectively. So therefore, from that understanding, we get that the circumference angle is half of this. Okay, and similarly with this, right? It can be a bit skew. Similar concept. Cool. Yeah, let's label this A, B, C, D, and then that's O, the center is O. Okay, so cool, keep that in mind. Let's do another like weird one. So let's look at this one, right? Chord AB, again, I'm not going to draw it in. Maybe let's do dotted lines. Okay, chord AB, firstly, it subtends, because we can follow along, right? It subtends O. Okay, then chord AB also subtends C. Okay, so the reason this looks weird is because the angle that it subtends at C, one of the lines, okay, goes straight through the center. So it looks like a center angle, but it goes through it to form a diameter. Okay, so one of them is a diameter, and that's why it looks like this. Okay, but again, it's still the same concept. So if this is 2x, this is x. Center angles are equal to 2 times that of the circumference angles. Okay. So now, I hope that makes sense. Let's move on to the next ruling. Okay. What happens if we have this example and we want to solve for the value of C, or we'll call it theta. Okay. So you might think, let's draw this. Chord AB, right? Now, chord AB subtends an angle at O. Okay, it's this angle here. So if we, okay, it subtends that angle. But if we kind of flip AB, if we don't look at the top half of AB, we look at the bottom half. So remember, it separates into segments. So AB separates us into this segment and this segment. Okay, separates it into those two segments. So in the top segment, right, we have that center angle at O. Okay, and then in the bottom segment, one could argue this is a circumference angle of AB. Theta is actually a circumference angle of AB, and that is correct, 100%. Theta is actually a circumference angle of AB. However, it is not in the same segment as the center angle. This center angle is in this segment. Okay, so because of that, the only ones we can work with regards to center angles have to be in the same segment. So angles like this, like this, like this, just act like they're perfect. Like this, all of these center angles, right? So those are the only ones we can work with, okay, because they're in the same segment. As soon as we go to the other segment, it doesn't just work like that. So for example, if this is 2x, then this here is not x. I know I'm putting x over x, but it's not x. It's not half of 2x. However, we can get it. Okay, we can get its value. Okay, so here let's solve for D and let's solve for C. They want us to solve for D and they want us to solve for C. So firstly, you need to understand that, okay, O is the center of the circle, right? For now, we'll just assume that in the question they will tell you. So AB subtends, okay, it subtends angles in two different segments. So let's just draw a dotted line for AB. Okay, so AB subtends a center angle at O called 2x, and in the same segment, it also subtends a circumference angle, which is going to be half of it, which is going to be x. Right, but now we need to still determine C. Now, how do we determine C? C is easy to determine. How we actually work it, okay, is instead of using this angle, we use the reflex angle at O, which is this angle here. The reflex angle, okay, because now in that case, right, the reflex angle is actually going to be the center angle for this angle here. A bit strange, but yes. Okay, so the reflex angle, reflex means around a point. Does it? Okay, either way, this reflex angle is going to be 360 degrees minus 2x because it's angles around the point, right? And this part here is 2x, so its reflex angle is 360 minus 2x. Okay, and then what we do is this 360 minus 2x, again, this becomes the center angle. And then this here becomes the circumference angle. Okay, this is the center angle, this is circumference angle. And how do you get from 1 to 1? Theta is equal to 360 minus 2x divided by 2. So theta is equal to 180 minus x. Okay, I hope that makes sense. So again, if you're dealing with the circumference angle in a different segment, this is how you deal with it. Okay, you need to work out the reflex angle at center and then half the reflex angle at center to get that angle of circumference, which is in the other segment. Okay, so here in this case, for example, excuse me, let's just do values. Let's just give values. 120. Okay, let's just say the angle here is 120. And they want us to determine C and D. So D is easy to determine because D is half of O. D is O. Sorry, D is 60. Sorry. Half of 120. We say 120 divided by 2. So let's write that actually. And you'd give your reason. Do I give you a reason? Yeah, sure. We can say, you can use that reason that they give angles at center equals 2 times angles at circumference. Okay. And thereafter, what we can also do is to get C. Remember, C is now the angle in the other segment. So the way we do that is we calculate the reflex angle. The reflex angle here is going to be 360 minus 120, which is equal to 240 degrees. And then that 240 degrees, we then half it to give us C. C is equal to 240 over 2. Equal to 120. So will it be, so then will it be 180 minus angle C? Not sure I understand exactly what you mean. Not 180 minus C, it's 180 minus, this here becomes 360 over 2, which is 180, and then 2x over 2, which is x. I'm not sure if that's what you're asking. Okay, but here's the answer. This should be 180 minus x, and this is going to be, because we have values, it's actually 120. Okay, if you'd like, please try and rephrase your question so I can understand it, and I can try and answer it. But okay, nevertheless, let's continue, right? So we're done with theorem 2, theorem 1, theorem 2, line from center perpendicular to chord, line chord which bisects, the line from center bisects the chord perpendicular to chord. Okay, so let's move, and we did theorem 2, angles at center is equal to 2 times angle at circumference. By the way, the things that are highlighted are the reasonings that you can use in your brackets, because I'm sure by now you know that in Euclidean geometry, right, for your reasons, you always need to give reasons. Okay, so those are the reasons you give. They are highlighted in yellow. Let's look at theorem 3. Theorem 3 says angle in a semicircle. The angle subtended by the diameter at the circumference of a circle is a right angle. Okay, if a chord subtends an angle of 90 degrees at the circumference of a circle, if a chord subtends an angle at 90 degrees at the circumference of a circle, then that chord is the diameter of the circle. If B is equal to, okay, so let's discuss this. Okay, so all they're saying is, remember we learned about chords, right? We learned about chords. Now you get a special type of chord called the diameter, of course, right? The diameter is also a chord. Okay, it's just a chord that happens to pass through the center. So this is a random chord. That's not the diameter, doesn't pass through the circle. However, if we have a chord, okay, if we have a chord that happens to pass through the center, then of course this would form 2 radii, and the entire thing is a diameter. Okay, so basically when we have any angle which is subtended by the diameter, so it says angle subtended by the diameter at the circumference of a circle is a right angle. So any angle subtended by the diameter, okay, obviously at the circumference, is equal to 90 degrees. So it's perpendicular. So here angle B is 90 degrees. Okay, and here they are saying that the inverse or the converse of it, so now we can understand it. If a chord subtends an angle at 90 degrees at the circumference of a circle, then the chord is the diameter. So just say we don't know. The question is AC the diameter? Let's say the question doesn't specify, because again, the question has to specify. If AC is the diameter, it has to specify. If it doesn't, then we can't assume that it is. Okay, so just keep that in mind. So what's given here, okay, is that these two are perpendicular. Sorry, no. Sorry. What's given, yes, this is given. What's given is that this is perpendicular to that. Okay. But the question is AC the diameter? That's what's unknown. We don't know if AC is the diameter. Okay. And obviously we don't know whether M is the center or not. Okay. So the question is AC the diameter? So the way you'd need to prove that, okay, you'll see there's a lot of proofs in this topic. The way you need to prove that, if you can prove that B is 90, then you definitely know that AC is the diameter. So that's why we call it the converse. It's the opposite. Because if we work forwards, okay, if we work forward like normal, we would say, okay, if we have a diameter and any angle subtended by that diameter is 90. But now what happens if we don't know if it's a diameter? If we can prove that this specific chord subtends a 90-degree angle, then that chord is definitely the diameter. Okay, that chord is definitely the diameter. Okay, so that's what the converse is. It like reverses all of these. Okay, it's like the backwards version. Okay, so just like how when you have a diameter, you know you can conclude that it subtends a 90-degree angle. If a chord in a circle subtends a 90-degree angle, you can also conclude that that chord has to be the diameter. Okay, so just keep that in mind. Also, just remember, okay, any angle subtended by a diameter is 90. So that angle is 90. What happens if I subtend a different angle? This one is also 90. Okay. What happens if I subtend a third angle? This is also 90. Okay, and you'll remember, right, remember angles subtended by the same chord are equal, and the same chord is the diameters, and it's all equal to 90 as well. So it'll be 180. So why do you half it? It's not subtended by the same chord because it's by different. Okay, we'll go back there. Let me do one more theorem and we'll go back there and I'll explain it again. Okay, but for now, let's look through this theorem 4. The reasoning for theorem 4 is angles in the same segment. Okay, so we kind of already discussed this, but let's go through it formally, right? It says angles subtended by a chord or an arc at the circumference of a circle on the same side of the chord are equal. Okay, so let's do it with our little own example here because the example is skew. Okay, so we discussed this. And I'll show you how. We have chord AB. Okay. And we have chord AB subtending this angle for us. Shucks. Okay, let's do this. Subtending this angle for us, and also subtending this angle for us. Okay, and we discussed that they're equal. Okay, because they're angles subtended by the same chord. And essentially, this theorem is that's what we're learning. So we call this theta. We call this theta. We know that why are they equal? Because they are subtended by the same chord. Okay, since the chord, again, the chord is equal to each other, right? If you're considering the chord for AB, it's like, again, it's like the same thing if you did in two different circles, right? If you did the green in one circle and you did the red in one circle, but you'd use the same equal chord, okay? So in this case, again, we're using one chord, okay, and subtending two different angles, and we need to know that those angles are equal. Okay, so again, like I said, that's basically what the theorem states, but the reason is angle in the same segment. Okay, and that's important. Why is it called angles in the same segment? Now we know, because we can see that this chord actually separates this circle into two different segments. And the angles that are equal to one another are actually in the same segment. Because if we had to draw, let's just say we had to draw the green angle at the bottom. Okay, let's just say we have to draw the green angle at the bottom. This is not equal to theta. They're not equal because, yes, angles drawn from the same chord are equal, but they have to be in the same segment. So that's actually why the reasoning we have is angles in the same segment. Okay, if we look at there and they form yeah, like this sort of shape. Okay, like a zigzag type thing. Okay, if we have to look at the example, we can see that we have which chord we actually work with. We work with chord RT. Okay, and RT actually subtends angle M and angle P. Okay, RT subtends angle M and angle P. And since it's subtended by the same chord within the same segment, they're equal to one another. Okay, yeah, they say it, yeah. RPT is equal to RMT. Okay, and then the converse of it, okay, line substitutes is equal to angles. Okay, if a line segment joining 2 points subtends equal angles at other 2 points on the same side of the line segment, these 4 points are consecutive. This is why, okay. So basically it's the converse of it. So in this case, instead of being given what? Instead of being given the fact that it's in a circle and it's subtended by the same chord, what we can conclude, okay, is if we are given the fact that we can see that W and U are subtended by chord YZ, okay, and it's given that they are equal, okay, that W is equal to U, okay. In this case, since W is equal to U subtended by the same chord, we can therefore say that this is concyclic, meaning that this actually these points, all 4 points would fit on a circle. All 4 points touch on the edge of the on the circumference of a circle. Okay, this one is not so important. So if you don't understand this specific one, it's okay, because we will revisit this concept when we do cyclic quads, and there it makes more sense, right? When you're required to prove a cyclic quad. So don't stress about this too much. But this one you should understand, right? The basic way going forward, okay, of how angles in the same segment or angles subtended by the same chord within the same segment are equal. Okay, let's just go through this again. You half it if it's not subtended by the same chord, because it's by different segments in the circle. Okay, so basically, look, we're considering, okay, chord AB, right? Now, chord AB separates the circle into 2 segments, and angles could be subtended in either segment. Okay, so if we have to get rid of this, right, we can see that AB subtends a center angle and a circumference angle in the top segment. However, if we introduce our bottom segment again, we can further see that AB also subtends an angle in the bottom segment. Okay, so the first direct way is not going to work, meaning angle at center is equal to 2 times angle at circumference. Okay, so AB subtends this center angle in that segment, and it also subtends that circumference angle. So therefore, this angle, D's circumference angle, is half of the center angle, because those are in the same segment. Okay. However, you see the tricky part is the fact that AB still subtends C. So there has to be a way for us to utilize this theorem to calculate C, provided that we have the center angle. Because remember, you cannot have another center here and then that doesn't work, right? You can't have another center here to say, okay, we have a center in that segment and we have a center in that segment. That doesn't really work, right? So there has to be a way for us to use the same center of the circle, even though we're in a different segment, we're still in the same circle. Okay, so there has to be a way for us to be able to use the theorem of angles at center is equal to 2 times angle at circumference with the center that we work with, and that's the way that we use. Okay, the way we use is that the regular angle, okay, that's found within the same segment, the regular center angle that's found within the same segment, okay, that can help us to determine the circumference angle within the same segment. Okay, I hope that makes sense. The angle, the center angle that's in the same segment, we just divide that by 2 to give us the circumference angle in the same segment. However, the circumference angle, which is not, the circumference angle which is not in the same segment, that is, just remember it, by heart it, don't question it. Like, there's no need to question it, because you won't, a further understanding of this is not needed. Like, this is the furthest you need to understand of it. Okay, that this circumference angle, again still subtended by AB, can be calculated by the reflex angle, Okay. Okay. The reflex angle at the center of the angle, the reflex angle basically subtended by AB, because this reflex angle at O is technically subtended by AB because it's part of this chord. It's subtended from this chord AB, and its reflex angle here, this is the reflex angle. Okay, its reflex angle here at O, okay, is again, it's technically subtended by AB. And this reflex angle is actually what we would refer to as the center angle of the circumference angle in the other segment. Okay, so yes, I hope that explains it. Okay, but yeah, let us conclude there. I'm still going to leave it open for a few minutes for anyone who has any questions, but I just want to end it formally. So for those of you who need to leave, you are free to leave. And those of you who have questions or want to stay behind to hear others' questions, you may stay behind. But yeah, thank you guys so much for joining. Jazakallah khair. Assalamu alaikum. I will see you guys next week. We will continue with this. Okay, assalamu alaikum and goodbye. Okay, but yeah, it's going to be open for the next 2 minutes or so. So if you do have any questions, and the person who asked this specific question for me to revise this, let me know if you understand it or if there's still something that's confusing you, and I can address it now. I've been absent for days because I suppose they were very fast with topics. Okay, that's fine. That's why I suppose hopefully I try my best to not go too fast, try to go through every concept. So hopefully you can gain a better understanding from here. Or you can't give them from, are we going a bit too fast? Okay, so okay, so what I would recommend is try rewatching the video. Right, try going through these concepts, reading these concepts on your own. Okay, try and getting an understanding for yourself to see what's going on, and then perhaps maybe rewatching the video to see my explanation thereafter. Okay, so try and, like I said, try and make sense of it by reading it through it on your own, and then watch an explanation to clarify any of your misconceptions. Okay, but I try to go as slow as possible. No problem, you're welcome. Okay, I'm glad you understand. That's good, Shanique. Okay, cool. But I don't think anyone else has any other questions, so let's end it there. If you guys do have any other questions, just message me, and if I forget to message you, just remind me, like reply again or something to remind me, and then hopefully I'll get back to you. It's been a bit crazy, but yeah, I try my best. Okay, perfect. Thank you guys so much for joining again. Once again, I will see you guys then next week. Have a good rest of your weekend. I'll see you guys tomorrow, actually, for those of you